Welcome everyone to the Thursday morning science webinar. Our guest today is Professor Mauricio Bustamante from the Niels Bohr Institute of the University of Copenhagen. Mauricio Bustamante is a theoretical astroparticle physicist, but he's also very interested in experimental results, as I hope he will also talk about. So about his career and his education, he did his undergraduate and master studies at the Pontificia Universidad Católica del Perú, and then he did his PhD at the University of Würzburg and at Desi Zeuthen in Germany, where we also had the opportunity to meet and to collaborate for a while. After that, he was a postdoc, first at the Center for Cosmology and Astroparticle Physics of the Ohio State University, and then at the Niels Bohr Institute, where he is now a faculty member. So his interests and the interests of his group are mostly related to cosmic neutrinos at the highest energies. About this, of course, one of the main interests is to push particle physics, is to use these results and these studies to study also particle physics in regimes that are not reachable by particle accelerators which are built on the Earth. So also with the goal of discovering some new physics maybe. So today we are going to listen about the physics of neutrinos with the talk that Mauricio has prepared for us. And so I thank him very much for accepting our invitation, and then I let him start his presentation. Thanks a lot, Mauricio, for being here.
Thank you, Denise, and thank you, Marco, and thank you, everybody. Welcome, everyone. Thanks for being here. I'm going to share my screen now. That should do it. Let's see, I'm going to go full screen. There you go. All right. All right. Every second of every day of your life, 100 billion, so that's 10 to the 11, invisible, nearly massless particles traveling at close to the speed of light will cross every square centimeter of your body. And that happens to every one of us. These particles, in the number they come from every direction. But I want you to really grasp the magnitude of 10 to the
Mauricio, I think your microphone is muted.
We don't hear.
Sorry, it got muted again when I started. Let me restart then. Thanks for letting me know. All right, I will resume. Okay, is that better?
Yes, now it works.
Perfect. Sorry about that. All right. So every second of your life, 100 billion invisible particles, nearly massless and traveling at close to the speed of light, will cross every square centimeter of your body. 100 billion is a huge number. It's about 15 times the number of people alive on Earth right now. It's about the number of cells in the human body, about the number of stars in the Milky Way, and about the number of galaxies in the observable universe. So it's a really large number. Throughout your life, these particles will go through you, and only maybe one or two of them will actually collide with you. So why do these particles, which we, as we will see, called neutrinos, that basically don't interact with anything most of the time, why are they so important? Why do we pay so much attention to them? And the reason is that even though they are nearly not there, they actually bring information from places that would otherwise be impenetrable, would be opaque to us. High density places, very far away places, places that are hidden from electromagnetic signals, so no light can come out of them. And so many times, neutrinos are the only ones that can actually bring us information from parts that would otherwise be unknown. They come, for instance, from nuclear plants, the cores of nuclear plants, which we cannot image directly. They come from the decay of radioactive elements in the crust of the Earth. They come from the core of the sun that we cannot see directly. They come even from very far away places, like both inside and outside our own galaxy. And so in this talk, what I want to show you is like a wide overview of why neutrinos have these exceptional properties. Why do they matter? What we have learned over the past 80 or so years about them, at what we're learning and what we will learn over the next 10 or 20 years. So let's start from the top. All the matter, at least the normal particle, is made up of the usual suspects: neutrons, protons, and electrons, in different combinations, of course. We know after almost a century of particle physics that neutrons and protons themselves, they're built of smaller particles that are called quarks, and they're built of two types of quarks called up and down quarks. And electrons, as far as we know, are not made up of anything. We'll see that these particles talk to one another. They interact via four fundamental forces. We call them electromagnetism, the one that we more familiar with, and they are that force is carried by a photon, which we call the carriers of the forces gauge bosons. The strong interaction is the one that keeps quarks together in protons and neutrons. And then there's an extra interaction, which will be the most relevant for us, and we call that the weak interaction. And there are three different carriers for the weak interaction: the Z boson, the W plus boson, the W minus boson. So this is where neutrinos come in. Neutrinos, as we will see, they're related to electrons, and they will talk to electrons and to the rest of the matter by exchanging with that matter these weak gauge bosons. And because they're weak, I want you to focus on the word weak, because that's precisely why they're so difficult to detect, and that's precisely why they go through us almost without interacting. Now, nature is a bit more complicated than that. It won't matter very much to us, but there's two copies of the quarks. There's not only up and down, but there's heavier quarks that don't make up normal matter. But there's also two copies of the electron that are heavier than the electron, and they're called the muon and the tau. And each one of these comes with its own neutrino. And we'll see that the fact that there are three different types of neutrinos is actually relevant and interesting, and we'll come to that. And then finally, there's the Higgs boson over there that gives mass to most of these particles. Okay, so let's see why we thought about the neutrino in the first place. And again, let's focus on the proton, the neutron, and electrons, and they get together and they make atoms. The simplest one we can make is a hydrogen atom. So we can get a H11, just a proton and an electron. That's a stable atom. If we add a neutron, we got a deuterium, and that's also stable. If we add an extra neutron, we get tritium, and tritium is no longer stable. It's unstable. It decays after about 16 years. So why does it decay? And the reason why it decays is that the neutron in the wild, when it's not inside an atomic nucleus, it only lives for about 15 minutes before disintegrating and decaying into a proton, an electron, and we will see something else. This process is called beta decay. It's one of the forms of radioactivity. Prior to 1930, or I should say at the beginning of the 1930s, there was a problem with how we understood beta decay. So you see that there is an electron that's coming out and a proton that's coming out, and those are the only two particles other than the neutron that we knew of back then. So we thought that the neutron was decaying into what we call in particle physics a two-body decay. There was only two final state products, the electron and the proton. And it turns out that if we know what the electron mass is and the proton mass is and the neutron mass is, and we knew back then what it was, we can calculate exactly what the energy of the electron should be when the neutron decays. So we can go to an experiment and compare our prediction to the energy that we can measure of the decayed electron when we get together a lot of neutrons that decay. And we did that, and we expected than to have electrons always with the same energy. So we expected what you see there on the left, that the energy of the electron was always the same regardless of how many times we repeated the experiment and measured the energy of the electron. But actually what we measured is different. We saw a distribution in the energy of the electron, and the highest energy more or less coincided with what we expected for what the energy of the electron should be, but there was a continuum of energies below that one. And it turns out, again, that if we have an extra particle in the decay, that could actually solve the problem. So what I'm saying is that now, initially we thought that the neutron was decayed into an electron and a proton, but it turns out that that didn't work because the electron had a distribution of energies instead of a fixed energy. However, if we added an extra particle, then the final state energy of the electron was no longer precisely determined in every single one of the decays, but actually had a certain probability distribution, which coincided with the one that we were actually looking at in the experiments. And that particle was called the neutrino. So the neutrino was a last-ditch attempt to explain the beta decay and the energy spectrum of the electrons that come out of the decay of the neutrons. It was proposed, as I said, in 1930 by Wolfgang Pauli, to his regret, because that particle, the neutrino, had to be neutral, electrically neutral, so it didn't interact with our normal detectors back then. It had to have very small mass or be massless, because otherwise there wouldn't be enough energy to create the electrons and the protons in the decay of the neutrons. Remember, we're creating new particles, and if the neutrino requires a lot of particles to be created, then there's not much left over to create electrons and protons. So he proposed a particle that was nearly or maybe completely undetectable. However, it did solve the problem of neutron decay, and in the years after that proposal, Enrico Fermi actually developed a theory of the neutron beta decay that included the neutrino, and it works pretty well, at least for a few years. So neutrinos are very light, as I said, and very antisocial. In a plot where in the x-axis we plot the masses of particles, and the y-axis we plot how interactive it is, of how prone it is to talk to other particles, then the neutrino is actually in the corner at the bottom left. So it's the lightest particle with a mass that we know of. I'm giving some spoilers here. We now know that neutrinos have mass, but it's so small that we don't know how small it is. And out of the particles that we know of, it's the one that interacts the most weakly, compared to the photons and the electrons and the protons and anything else. There's dark matter in there, but we don't know what dark matter is. I'm just putting it there for reference. If it exists as a particle, it has to be even less interacting with the neutrino. So to give some numbers, how weak do we mean by weak? So again, there's four interactions, fundamental interactions: is the strong electromagnetism, weak, and gravity. And let me just show you the relative strength. So this is the strength that two protons close to each other would feel via each one of these four interactions. And as, this is a relative strength, so as a reference, let me say that the strong interaction has a strength of 1. If that's the case, gravity is always the weakest one, and it usually doesn't matter for any fundamental particle processes. It matters at very large scales only. Electromagnetism is about 100, the strength of the strong interaction, and the weak interaction is 10 to the minus 13 times the strength of the strong interaction. So it is really weak. The only thing that is weaker than that is gravity. Of course, there's a caveat here that the strong interaction is strong, but it only acts in very small scales. The electromagnetism acts at infinity scale, so it just becomes weaker and weaker the farther away we go away from the sources. The same is true for gravity. And again, the weak interaction acts only at very, very small scale. So it acts only in close range fundamental particle processes. And that's the actual interaction that we will be interested in, because that's the interaction that neutrinos are sensitive to. In fact, that's the only interaction that they're sensitive to. So just as a reference, let's imagine what it would take to stop neutrinos knowing that they are almost non-interacting. Just imagine that you have a flashlight and you shine the light to a wall. The light is almost immediately stopped as soon as it hits the wall. If you, instead of a flashlight, have a beam of protons from your particle accelerator, if they're very energetic protons, they will penetrate some of the wall, but that's it. They will get stopped. They quickly interact electromagnetically and just make a little dent in the wall. If you have a neutrino, it would take about 1 light year of lead in order for a neutrino to be stopped, because unlike the protons and the light, they don't interact electromagnetically, they only interact weakly. However, at high energies, they do get stopped occasionally by interacting with matter. And in fact, when we see high energy neutrinos coming from one side of the Earth, going through it, there is a sizable attenuation of their number as they go through the Earth. So we don't get the same number of neutrinos if we look at them from the opposite side of the Earth, because some of them will actually get stopped while traveling inside. All right, so we know now that neutrinos are very light. As far as we know, initially they were even proposed to be massless. They are very weakly interacting. So how do we know they're real? So far, they're hypothetical particles that are almost undetectable. And so how do you detect the undetectable? Remember, the initial motivation was to explain the beta decay of neutrons. We can repurpose that reaction. For those of you that have taken particle physics, think about crossing symmetry. So now we have a neutrino interacting with a proton, and out comes a positron, that's an anti-electron, and a neutron. So I just rearranged the diagram on the left to give the diagram on the right. And we call that process inverse beta decay. So what does this mean? It means that we have a beam of neutrinos and we point it at a vat of protons. Then we end up with positrons and neutrons that we might detect. And that's precisely how neutrino detectors, at least most of them, work. So the key thing here is that we're talking about a positron in the final state of this reaction. And remember that matter and antimatter, when they find each other, they annihilate and they create light. And that will be our signal. All right, so let's think about our toy experiment. We have a neutrino source that is making neutrinos, and we have a water tank. A water tank is just a lot of protons floating around. So we shoot neutrinos from the neutrino source. This can be, for instance, a radioactive source that we place somewhere. And most of the neutrinos will go through the vat of water and just go through it and don't interact. But occasionally, one of them will. And when that happens, it's because there was an inverse beta decay process. A neutrino came in, collided into a proton, created a positron and a neutron. The positron quickly finds one of the electrons that is floating around in the water, and annihilates and creates a quick flash of light, 2 photons, 2 gamma rays. That if you have photo sensors inside your water tank, you can detect that flash of light. And the neutron that is created is also floating around, and a few microseconds later gets captured by one of the atoms in the water. And when it gets captured, it creates another flash of light. So every time you see a quick succession of 2 flashes of light separated by about 5 microseconds, then you can claim that you have seen one neutrino. Now, of course, you cannot claim detection or discovery of neutrinos just by one of these events. You want to increase the number as much as possible of your detected events. So how do you do that? You increase the number of the number of interacting neutrinos in the experiment is the following. It's a function of the chance that one neutrino interacts with one proton, and that's something given by nature. Remember the weak force that neutrino feels. That's what determines what the interaction between neutrinos and protons are. This is fixed. And for those of you that have taken particle physics, this is just the neutrino-proton cross-section. The second ingredient is the number of neutrinos that reach the tank. And that means that you want a very intense neutrino source that's making as many neutrinos as possible. Also, you want to place your water tank as close to the detector as possible, because the flux of neutrinos goes as 1/L² by Gauss' law. So put it as close as possible to the detector, to the source, sorry. And the second, you want to wait as long as possible. You want to be patient. The third ingredient is the number of target protons in the tank. Of course, the higher the number of targets, the higher the chances that neutrinos hit one of them. So you want to build big. And that's the recipe that was followed for the discovery of neutrinos back in 1956 when Cohen and Rines discovered a neutrino. They placed about a couple hundred liters of water inside a tank, instrumented with photosensors, with photomultipliers, and they placed it about 10 meters away from a nuclear reactor. That's the equivalent of placing your ear next to a loudspeaker in a concert. So the number of neutrinos was very, very high. And they actually detected about 3 neutrinos per hour. They ran the experiments for a few months. And this is how neutrinos went from being hypothetical to being real particles. A lot has happened, of course, between 1956 and now, and we'll talk about that in a second. But this is not the only source of neutrinos. In fact, reactors are not the only source of neutrinos, but you are a source of neutrinos. When we eat bananas or some other food that has potassium, some of it has radioactive potassium, that's potassium 40, and it has a half-life of about 1 billion years. Eventually, it decays, and when it does, it emits neutrinos. So a person that weighs about 70 kilograms will emit about 4,000 neutrinos from the radioactive decay of potassium every second. So, of course, you'll never feel it. More to our point, there's many natural sources of neutrinos. So neutrinos have strange properties, but they are not rare in nature at all. What you see here is a collection of the fluxes of neutrinos coming from different sources in nature. In the x-axis, you're seeing the energy of the neutrino. We measure energy in particle physics in units of electron volts. It's a very small unit. It's about 10 to the minus 19 joules. So 10 to the 12 electron volts is about the kinetic energy of a flying mosquito, and about 6 times 10 to the 20 electron volts is the energy that 100 watt bulb emits if it's lit for 1 second. So we're talking about very small numbers. And in the y-axis, you see the flux of neutrinos that reaches Earth. So the number of neutrinos that reaches Earth per square centimeter per second per radian per interval of energy. All the way to the left are neutrinos that are left over from the Big Bang. They're very abundant, but they're very low energy and very difficult to detect. And in fact, we haven't detected them so far. They should be there. About the middle energies are the neutrinos that we're more familiar with. There's neutrinos created by the sun, by supernovas, so by star explosions when they reach the end of their life, by the reactors, nuclear reactors, and by the atmospheric creation of neutrinos by cosmic rays hitting the upper atmosphere. And we'll talk about this later on. At even higher energies, there are neutrinos coming from astrophysical sources, which might be even extragalactic sources, so sources beyond our Milky Way. And we've seen these as well, but they are more rare. And at the very, very high energies are what we call cosmogenic neutrinos. These are the ultimate neutrino energies that we expect. Again, they should be there, but their flux is so low that we have not seen them so far. And we expect to see them maybe in the next 10 to 20 years when experiments get better. Okay, so I told you that neutrinos are, now that they're real, they're actually extremely good tools for getting information to us from places that would otherwise be obscure to us. And my favorite example is the sun. So in the sun, nuclear fusion reactions are the ones that are keeping it hot. But this is a recent finding. Before the early to mid 20th century, we didn't really know how the sun worked, how it kept hot. If it was burning coal, it would have lasted only about a few thousand years. And we knew from geological records that the Earth was far older than that. And it was not until the development of atomic and nuclear physics that we found the solution, and that is nuclear fusion. In nuclear fusion, 4 protons get together, form 2 heliums, and they release some energy. But that's not the only thing they produce. They also produce neutrinos. About 98% of the energy goes into light, into energy, and about 2% goes into neutrinos. And we can see those neutrinos. In fact, there's many different nuclear processes in the chain of reactions that goes from 4 protons to 2 heliums that make neutrinos as final products of different energies. What you see here is the fluxes of neutrinos created by each one of these reactions. And the most popular ones, the ones that we've studied the most, are the ones coming from the decay of beryllium-7, from the decay of beryllium-8. And each one of these are have their own experiments and their own difficulties, but we've seen many of these. Now, neutrinos are made together with the light in the inner core of the sun. That is the inner, let's say, 10 or so % of the total radius of the sun. When the photons are produced by the nuclear reactions over there, they don't immediately leave the sun and come to us. They stay in there, bouncing around in the dense matter for a few thousand years. It's only after a few thousand years that they reach the surface and then travel the 150 million kilometers to us and then shine on us. So we cannot really see the photons directly as they are produced in the core of the sun. The photons that we get at Earth are, in a way, old photons. Neutrinos, on the other hand, produced in the inner 10% or so of the sun, as soon as they're produced, they almost free stream out. They take a few seconds to reach the surface, and then they get to us. So if we were to detect neutrinos, we would be doing 2 things. First, we would be actually proving that the sun is keeping itself hot by nuclear fusion. The second, we would be getting information from the inner core of the sun that we could otherwise not get. Now, this is easier said than done, and neutrino astronomy exists, but it's a bit different. We need to go underground. The reason why we need to build our neutrino detectors underground is that we have a very strong prevalent background of things that could mimic the signal made by a neutrino, but that if we place our detectors underground, this background actually dies out pretty quickly. To be more concrete, I mentioned earlier cosmic rays. These are charged particles that come from outer space. When they reach the upper atmosphere, they interact with the atmosphere. Think about an incoming proton, an incoming cosmic ray proton, interacts with the atmosphere, starts a particle shower. So it creates some intermediate particles. One of them is the pion. It's a very short-lived particle. It also creates neutrons. The pion decays quickly, and when it decays, it creates neutrinos on the one hand, that will become important later, but also muons, the heavier cousins of the electrons. And there's other products in between as well. So these muons, if we were to place our water tank that detects neutrinos on the surface, we will be flooded with muons that would look like neutrinos, but aren't really neutrinos. And it would be difficult to distinguish this background from the actual signal of neutrinos that we're looking for. So we place the detectors underground because about a kilometer of Earth is sufficient to stop most of the muons. And then we end up with a cleaner signal that is due mostly to neutrinos. So that's how solar neutrinos got actually detected. And solar neutrino detectors look kind of like this. They're big, again, water tanks, now placed inside caverns or under mountains. In this case, this is Super Copenaghen. This is 50 megatons of water. We're not talking about 200 liters anymore. These are huge experiments. This is a vessel, as I said, surrounded by photomultipliers, detecting neutrinos by inverse beta decay. Inside, it looks like this when it's not filled with water. And each one of the photomultipliers it looks like this. So if you turn it on, wait for about 400 days, and are very good at cleaning your background, you end up with a photograph of the sun as seen in neutrinos. This is an actual photograph of the sun, not taken with light, but taken with neutrinos. The sun is somewhere there in the center, where the neutrino emission is the highest. So what did we learn by detecting neutrinos from the sun? As I said, first, we actually now know how the sun keeps itself hot by nuclear fusion. Second, we know what the temperature at the core of the sun is. We didn't quite know this before. The reason is that the neutrino flux is a very strong function of the temperature at the core of the sun. It actually goes as temperature to the power of 24. as far as I know, there's no other physical quantity that has such a strong dependence on a variable. That means that if by measuring very precisely the neutrino flux, we also can measure the temperature pretty well. And in fact, it's about 15 million kelvins. So there you go. Neutrinos brought us information from the inner part of the sun that we otherwise wouldn't have had. Now, one extra thing that might catch your eye, and for me it sounds kind of like sci-fi, is using neutrinos to do tomography of the Earth. So I said earlier that neutrinos are not stalled by matter. That is true, but that becomes less true as the neutrino energy goes up. So the higher the neutrino energy, the higher the chances that the neutrino actually interacts with matter. And so we can use neutrinos made now in the cosmic ray interactions in the atmosphere, and they will cross the Earth, and they will reach a detector called IceCube, which I will talk more about, on the opposite side of the Earth, and they will cross the Earth across many different directions. So the ones that go through the whole diameter of the Earth or a sizable part of the Earth before reaching the detector in the South Pole, those are attenuated significantly as they go through the Earth and interact and get stopped. But the ones that come just from directly above IceCube, they do not get attenuated because they don't go through the Earth. They just go directly into the detector. So you can compare the flux of neutrinos coming from different directions into your detector, and from that alone, you can actually weight how much, you can actually find how much the Earth weighs, what is the mass of the Earth. Now, typically you would do that by using gravitational measurements and finding out what the mass of the Earth is, or by using celestial mechanics and finding out what the mass of the Earth is. But this measurement actually is not based on gravitational interactions of any sort. This is just a measurement of the Earth by using the weakest interaction that we know of, which is the weak fundamental interaction. And in fact, when you actually do the analysis with real data, you get a number for the Earth's mass that is about 6 times 10 to the 24 kilograms, which is in very good agreement with what you get with the usual gravitational measurements. So this is a measurement of the mass of the Earth using the weakest of the four fundamental, or the three relevant fundamental processes. Okay, so far I've shown you that neutrinos have unusual properties, but let me show you one of the most unusual properties, and that is neutrino oscillations. So neutrinos are they're what I like to call quintessential quantum particles. They do quantum mechanics over microscopic scales, which is a bit unexpected or oxymoronic. So let's take a step back. We have been talking about neutrinos, and these neutrinos have come in connection with the electrons. Remember the beta decay of neutrons ended up in an electron and neutrino. We call that neutrino that comes together with the electron neutrino. And we baptize as electron neutrino the type of neutrino that appears together with an electron. So every time you see a neutrino created with an electron, it's an electron neutrino. But as I said earlier, the electron has two heavier cousins, the muon and the tau. The muon has a mass 200 times higher. The tau has a mass of about 35 times higher than the electron. And each one of these comes with its own neutrino. So the mu neutrino comes with the muon, the tau neutrino comes with the tau. As far as we know, there are only 3 types of neutrinos. So one process that creates neutrinos, like the beta decay of neutrons, will create a neutrino with a given flavor, say electron flavor, and it's always that flavor. The neutrino travels for some distance between the neutrino source and the neutrino detector, but at the time that the neutrino is detected, it may no longer have the same flavor as that with which it was created with. It could be still an electron neutrino, but it could also be a mu neutrino or a tau neutrino. And this phenomenon is called flavor oscillations. It's a quantum phenomenon, and it actually got the Nobel Prize a couple of times. The very cool thing for me is that this is one of the few instances where we can actually use quantum mechanics to compute probabilities of things that happen over macroscopic distances. So the distance between the source and the detector can be meters, as we saw in the experiments, or hundreds of kilometers, or even light years or billions of light years. So in the following few slides, what I want to do is a bit of quantum mechanics without the math. And some of you might be familiar with some of the formalism. And if there's questions about it, just let me know. So again, a neutrino is, to understand what's going on, why this flavor of oscillations happen, we understand a neutrino of a given flavor to be a quantum superposition. That means that an electron neutrino, for instance, is made up of 3 other neutrinos that we call mass states. So every flavor state is made up of 3 mass states, and in different proportions. So for the electron neutrino, we know that it's about 65% of the new 1 state, 18% of the new 2 state, and 17% of the new 3 states. And these, of course, numbers add up to 1, and they're fixed by nature. That's just how the universe works. Now, flavor states are defined, have a definite flavor. In this case, the neutrino electron has an electron flavor, but they don't have a defined mass. Whereas the mass states have, each one of them, a defined mass. We call them M1, M2, and M3, but they don't have a defined flavor. They're made up of different flavors. So what this means is that if we had an apparatus to measure the mass of the electron neutrino, then if we did the experiment of measuring the mass 100 times, we would get the mass of new 1 65 times on average, the mass of new 2 18 times on average, and the mass of new 3 17 times on average. That's what this means. All right, so that's what we have. Let's drop the numbers. We typically just write some coefficients in there, call them U, and the new mu and the new tau, so the other 2 flavors of neutrinos, are also combinations of superpositions of the 3 mass states with different coefficients. That's why I'm using different subscripts. Or if you have taken quantum mechanics, you can see that this can also be written in this way. Okay, so the key aspect here is that new 1, new 2, and new 3, each one have different masses. So M1, M2, and M3 have different masses. And because they do, then they travel at different speeds. And if they do travel at different speeds, then that means that they acquire different coefficients while they propagate from the sources to the detectors. So in the same way that if you have a very heavy ball and you kick it, then you will move it a little bit. And if you have a very light ball and you kick it with the same energy, you will move it a lot. This is the same that here with the neutrinos of different masses. The heavier ones go slightly slower than the lighter ones. And when that happens, then by the rules of quantum mechanics, then if a neutrino is produced like this, it travels a distance L from the distance from the source to the detector, then it becomes something else. Each one of the mass states will acquire what we call a quantum phase. And that phase depends on how long it travels, so the size of L, and on the mass of the neutrino, M1 in this case. Same is true for nu 2, the same is true for nu 3. Again, those of you that have taken quantum mechanics will see that that exponent there is just the eigenstate of the Hamiltonian that controls the propagation of the mass states, and that the exponential itself is the solution to the Schrödinger equation. But that's irrelevant for here. So the neutrino that was produced as a nu E is now no longer a nu E, it's something else. And because it's something else, then there's a probability that this is detected as a different flavor. So let's make a thought experiment and start with, again, with a source that produces only nu E, only electron neutrinos, and a detector that can count the number of electron neutrinos and mu neutrinos separately that reaches the detector. And let's assume that the detector is mobile. We can put it closer to the source, where the distance between the source and the detector will be smaller, or far away if you move it away. And we can think about this in terms of a smaller travel time if it's closer, or a smaller distance if it's closer, or a longer travel time if it's far away. And we'll do a thought experiment that moves the detector farther or closer. So let's start with the flight time of the neutrino from the source to the detector is 0. And in this case, because there's a source that makes only nu E, we will only measure nu E in our first measurement. Now we move it a bit farther away. and we measure some number of electron neutrinos and some number of mu neutrinos. We move it farther away still. Again, we measure nu e and nu mu. We move it farther away, and then we make a measurement of nu e and nu mu. If we plot those measurements as a function of the flight time of the neutrino from the source to the detector, then at time 0, we only got electron neutrinos because we're right next to a source of electron neutrinos. So the relative number of mu neutrinos is 0. If we move it farther away, we get some mu neutrinos, farther away still, some more, farther away still, some more. We move it farther away. Now we actually start getting fewer mu neutrinos, and so on and so forth. And if we do it with a sufficient precision, then we actually find that the behavior is oscillatory. And that's what we call this phenomenon of neutrino oscillations. So a neutrino that was produced as a nu e can be detected as a nu mu, and the probability of detecting as a nu mu is actually changing with the distance that the neutrino travels from the source to the detector. Now, this is the key aspect. So this is interesting in itself, yes, but so what? We can again use the rules of quantum mechanics, which I won't show here, and find what the top probability is. And this is the probability that a neutrino born as a nu e gets detected as a nu mu. First thing is that the probability is oscillatory, as it should be. The second thing is that it depends on this quantity over here, delta m squared, and that is just the difference of the mass of the state 2 squared minus the mass of the state 1 squared. So there's one extra step here that I want to show you. This is the survival probability, so the probability that nu e does not change is just 1 minus the probability that it does. So this is survival, this is transition. But the interesting thing here is as follows. If the two masses of the mass states were 0, or if they were equal to one another, then that difference of masses squared would be 0. And if you plug in a 0 inside a sinusoidal function, you get 0 as the result. So this means that if the masses were 0 or equal, we wouldn't have seen neutrino oscillations, but we have seen neutrino oscillations, and therefore neutrinos have mass. And that's what earned Arthur McDonald and Takaki Kajita the Nobel Prize in 2015. So we have seen, and we continue seeing neutrino oscillations from many different experiments. We know that the differences in the masses squared are very small, order of 10 to the minus 4 electron volt squared, or slightly bigger than that. These are tiny, but we don't know what the masses are. We only know what the difference of the masses squared are. So we look at many different places to find these delta m squares from the data. We look at nuclear reactors that produce electron antineutrinos. That bar on top of the electron of the nu means antiparticle. And these experiments are sensitive to the survival probability of electron antineutrinos. So how many are left over once they leave the source. We also look at the sun again. The sun produces electron neutrinos, and we can then measure the number of electron neutrinos that survive and the number of mu neutrinos that are produced. We look at neutrinos made in particle accelerators, in this case DUNE, which is one that is under construction, which creates a beam of neutrinos on one side near Fermilab in the United States by colliding a particle beam of protons into a carbon target and creating neutrinos as a result. And the neutrinos travel 1,300 kilometers to a detector and get detected over there. This beam contains electron neutrinos, electron antineutrinos, muon neutrinos, and muon antineutrinos. And so the experiment DUNE that will detect them will be sensitive to the transition and survival probabilities of all of these. You might be wondering about nu tau. I haven't said anything about that. There was an experiment. Nu taus are particularly difficult to make because you need to make the very heavy cousin of the electron in order to get nu tau, sorry. And that's difficult. You need a lot of mass to make them. So OPERA was an experiment that used the beam neutrinos created in CERN and directed towards Gran Sasso. And there was a detector that actually detected nu taus directly, and that was sensitive to the nu mu to nu tau transition. But it's difficult to detect them, and it detected 5 nu taus successfully in 5 years. And finally, there's atmospheric neutrinos, the same ones that were the background earlier on for our underground experiments. We can also use the neutrinos made in that particle shower and as a signal to look for neutrino oscillations. Very well. Okay, so we now know that neutrinos have almost no mass. We know that they almost not interact. We know that they change their nature by flavor oscillations. And for the last bit, just let me quickly show you what's going on at the highest energy. So we've been talking about the lower energy, so the neutrinos that were here, intermediate energies. And there is the astrophysical neutrinos. Those are the ones that have high energy astrophysical neutrinos, I mean. Those are the ones that have been only fairly recently discovered. We don't know where they're coming from. We believe that they're coming from places like these, where neutrinos are being made in the active supermassive black holes, for instance, in the centers of other galaxies that are spewing out matter and accelerating protons at very high energies, and protons interact with the surrounding matter and create particles of very high energy, including neutrinos. So this is production of neutrinos not by a process like beta decay, but by a completely different process called photohadronic interaction. So we get a proton, very high energy, interacting with surrounding matter, for instance, other protons or surrounding light. It creates some intermediate particles. Those particles will decay, and when they decay, they make final state high energy neutrinos. So in this case, it's making mu neutrinos, electron neutrinos, and anti-mu neutrinos, and anti-electron neutrinos as well. In 2013, it was announced that these neutrinos, which we had been searching for decades, actually were real, and that's because there was a new detector called IceCube. This is now it's not a megaton detector; this is a gigaton detector in the ice of the South Pole. This is not a water tank; it's using the actual South Pole ice, and it has instrumented the ice with about 86 strings that contain photomultipliers or photodetectors. And when a neutrino comes in, it will interact in the ice, create a flash of light, and that flash of light is what IceCube sees as a signal that is showing the detection of a neutrino. So these are the most high energy neutrinos we've seen so far. We don't know exactly where they're coming from, but they're been firmly detected as having an astrophysical origin and most likely an origin outside the Milky Way. So as I said, we don't know where they're coming from, but we believe that it's in places like this, where there's an emission of matter at very high energies that could actually induce the production of very high energy neutrinos. There's a couple places that are the usual suspects for this kind of processes. One is active galactic nuclei. As I said, that's when a supermassive black hole is eating matter and spewing part of it out in jets. And if the jet is directed towards us, we can see the products out of that, both the light and the neutrinos coming out of that. Also, gamma ray bursts have similar morphology at a different scale. These are especially energetic supernova explosions, and when the jet is directed towards us, we see the light in gamma rays out of that. We believe that some of them could be also making neutrinos. We have not been successful yet in finding sources of neutrinos at these very high energies. We're talking about 10 to the 15 electron volts or so, except in one very promising occasion where we saw one blazar, one of these very jets from a supermassive black hole, that emitted gamma rays and neutrinos in coincidence. And we believe that that's a sign of these neutrinos being produced in the kind of processes that we believe should give rise to the highest energy particles. And this is ongoing. Most of the work is in trying to understand how this blazar could have made neutrinos. It is not immediately evident how to do that, and also try to find more instances where this could happen. So we don't know where these neutrinos are coming from at the very high energies. We only know that they come from very far away, and therefore from a long time ago. But we can already use them to do the two sides of the coin of astroparticle physics. On the one side, astrophysics, and on the other, particle physics. And neutrinos are what joins these two. So what makes these high energy cosmic neutrinos so exciting is that they have the highest energies that we know of. As I said, it's about 10 to the 15 electron volts. That's the highest we've gone so far. That means we can probe new physics, particle physics at new energy scales, and we can also probe the most energetic, most violent processes in the far universe. And on the other hand, these are the neutrinos that travel the longest distances. That means that they bring us information from the essentially the edge of the observable universe, and also that along the way they can acquire tiny deviations due to new physics effects. All right, so that's the current status of neutrino physics. Now, we hope that in the coming decade, we actually will be able to be sensitive to the even higher energy neutrinos. Over here, there's a number of experiments. These are very difficult to detect because the flux is so low. There's a number of experiments that are being built to target that, like IceCube 2, like radio detection of neutrinos, not in a water tank, but now by the radio emission of neutrinos as they interact in the atmosphere, or even detection of neutrinos from satellites looking into the Earth. So there's a lot that we have found. There's also a lot that we don't know. This is an incomplete list of that. We don't know why neutrinos are so light. We don't know if neutrinos are their own antiparticles. I haven't talked about that. We don't know if neutrinos are what role they play in the abundance of particles versus antiparticles in the universe. We don't know exactly how many neutrino flavors there are. We know there are at least 3. Is there extra stuff? We don't know where the high energy neutrinos come from. And we don't know if there's new physics lurking at these very high energies, but we have good ideas on all of them. And more importantly, there's a lot of experimental progress going on now. So I hope I showed you that in the intervening 80 or so years, we've gone from having a particle that was hypothetical, that came in to solve a crisis in particle physics, to actually making it a real particle, and to the particle becoming a tool for us to find things about the universe from the most distant sources that we know of, from the highest energies that we know of, and hopefully in the intervening years from now until the end of our careers, we'll actually have concrete solutions to some of the open questions that are still out there about neutrinos. So just to end up, let me advertise for those of you that are PhD students and advanced master students, we're organizing a summer school on neutrinos this July here at the Niels Bohr. And if you're interested, please just take a look at the webpage or contact me. There's no registration fee, no participation fee. We're planning this as an in-person event if it's possible to do it by then, but also there will be a live streaming, so you can also join that way. All right, thank you.
Thank you so much, Mauricio, for this very nice overview and summary of neutrino physics from also across the history of the experiments and of the theories. So thanks a lot. So before starting with the questions, I would like to just to remind, I think also some of the people maybe attending here are also interested, or maybe they already know that some of the results that you told us about neutrinos have been reached or have been studied also here at the Gran Sasso lab. So we are just a few kilometers away from the Gran Sasso mountain, and under the mountain there is this, the largest laboratory, the largest underground laboratory, which hosts several experiments, and among them we have Borexino, that is actually studying the neutrinos from the sun, as you also mentioned at some point, and also is also having some results about the tomography of the Earth with neutrinos, which is, I think it's very fascinating result. And then also you mentioned also Opera, which is now not more in operation, but it is always very fascinating for people who came to visit the underground lab to think that this neutrino beam is crossing the Earth for more than 700 kilometers, and then can be detected eventually as tau neutrinos, starting from muon neutrinos in the lab.
For sure. Yeah, Opera and Borexino were amazing experiments. Yeah.
So we have, we are also interested a lot in this physics here. So thanks a lot for bringing this or for explaining this so well. So let me start. I see some questions, so I can read them for you. Simone Rossoni is asking about the possibility to use neutrino oscillation to study matter-antimatter asymmetry. Can you comment on this?
Yes, for sure. So I didn't actually talk about that explicitly, but you are right. So let me maybe go back over here. Okay, so when you calculate the neutrino oscillations, the probability of neutrinos oscillating, let me go to just a minute here. The one I'm showing here is the probability of a new E going into a new mu. And we believe, because we believe in the charge parity time symmetry, we believe that that holds, and it's at the base of our particle physics building, that if we were to invert this, we did nu E bar into nu mu bar, this should look the same, this probability. And if we made a measurement, it would look the same. But if we actually measured nu mu bar going to nu E bar, then the difference between that process and this process, the nu E to nu mu, there's a difference, and that difference is telling us something about the CP violation of neutrinos, and that speaks to this matter-antimatter asymmetry that you're asking about. So there's, in the universe, there appears to be more matter than antimatter, and we don't know why. And that's actually one of the open questions in physics for a long time. And neutrinos seem to have some contribution towards that, but it's a small one as far as we know. So we're still trying to figure out what the contribution is, but we already know that even if it's as big as it can be, it will not be enough to explain the level of dominance of matter over antimatter that we observe in the universe. So it's an interesting question in itself, because it could reveal things about what quantities are conserved in fundamental physics and what quantities are broken. But we already know that it will not be enough to explain the observations of how much matter there is compared to antimatter. And one way to find, again, what the size of this CP violation is in neutrinos is by comparing the oscillations of neutrinos and of antineutrinos. And it's being done. It's a hard measurement, but it's being done.
Thanks for commenting on this. So next question is by Luca Giacchi, that is asking about the possibility to use neutrinos in other applications like communications or clinical diagnosis.
Yeah, that's an interesting question. There's not many applications. There was a paper now maybe 10 years ago from I want to say it was Minerva. That's one of the, maybe I'm getting it wrong. It was one of the Fermi-Lab neutrino experiments, and it was neutrinos created in a particle beam in an accelerator. They actually tried to send information like in bits by controlling the production of the neutrinos by controlling the collision times of the protons that give rise to the neutrinos. So they encoded some message, I think it was neutrino, in according to ASCII or something like that, by changing the times at which the protons would collide and therefore produce neutrinos. And then they detected those neutrinos in a detector some distance away, and they could decode the message by detecting the neutrinos. The bit rate was extremely low. In principle, if you had like an extremely intense neutrino beam, you could send messages from one end of the Earth to the other without relying on satellites. That is sci-fi so far. At some point, we even wrote a paper ourselves when I was like an undergrad or master's that we were trying to find whether we could tell if there is like overdensities of matter inside the crust of the Earth or not by shooting neutrinos through the crust. It can be done in principle. In practice, you need a super intense beam of neutrinos that is not available. As for medical or clinical diagnosis, there's no application at all. Neutrinos are too weak to do anything of that sort. Yeah.
Thanks. So I think this is next question is more or less on the same topic. So it is about if neutrinos can be used to develop any technology in the future?
Not as far as I know, other than a couple of good stories by Stanislav Lem, like that's science fiction. I don't know of any actual practical application of neutrinos. I want to say that we study neutrinos not because they have practical applications, but because they are revealing things about nature that nothing else could reveal to us. So this is a purely, let's say, curiosity that is driven us to study neutrinos. In between, of course, the technology that has been developed to make neutrinos and to detect neutrinos, that has spin-offs, as with everything, and that's useful in itself. Like you build better photomultipliers. When you're building the accelerators that make the protons that make the neutrinos, you get to build better magnets, etc. But neutrinos themselves, not so much.
But anyway, you told us about the history, basically, of particle physics. So neutrinos really enter in the history of the experiments of the last century, with which we could understand, I mean, how the matter and how the interactions work. So this is already by itself very relevant, even though it might seem it doesn't have any application. But this, I mean, the knowledge of what. Yeah.
Absolutely. So, maybe before Marco's question, I've just read it. Yeah. Let me show you, just to stress your point, Denise, just one thing that I actually skipped, and that is when we're talking about these very high energy neutrinos made in these supermassive black holes or things like that, the neutrinos are not the only things that get produced. You also get electrons and photons in the form of gamma rays and neutrons and protons emitted. So in the last few years, this new paradigm of multimesssenger astrophysics has been emerging, and that is what I believe is like having a cinema projector and 3 different films, each one carrying a different color, like a Technicolor thing. So one of them actually projects the information in radio, infrared, or optical emission. The other is high energy emission, like X-rays and gamma rays. The other is neutrinos, and the other is gravitational waves. And only by looking at all of these, we get the full picture of these very intense, very exotic astrophysical sources. And in fact, that has already started to happen. In 2017, we got the first multimesssenger detection of emerging of 2 neutron stars. We saw the gravitational waves from them. We saw the infrared and optical emission from them. We saw gamma rays from them, and we saw actually many other wavelengths. We didn't see neutrinos this time, but it might happen in the future. And with all of these, we actually got a good picture of what this looks like. So yes, there's no practical applications, but the amount of information that neutrinos can bring in completing our view of the universe is, it's massive. Yeah.
Yeah. So I was actually going to ask you to comment about multi-messenger astrophysics. So thanks for this.
Thanks.
And what is also, I think, very fascinating is that these different aspects of physics and astrophysics are put together thanks to, I mean, we are putting together the microscopic world thanks to these particles to understand what is huge, like this, I don't know, galaxies or whatever other things that emit these particles and light. So this is very relevant. I mean, this aspect of putting together different results. So next question is by Marco, that is advertising that this is a naive question, but I think it is perfect. It is fitting very nice, this discussion. So he's asking if there is anything that can affect neutrino oscillation. For example, is the frequency of oscillation maintained over astronomical distances?
Yeah, this is not a naive question at all. This is a very good question. So let me start by saying that I made a few simplifications in my explanations of neutrino oscillations. So yes, neutrinos are typically, at least at low energies, are typically not affected by the matter that they go through, but they still, in a way, feel it. And so think about swimming in a pool of water versus swimming in a pool of honey. You will feel some drag, a higher drag when you are swimming in a pool of honey. So when neutrinos are moving in a high density environment, they can still stream out of that environment more easily than light and anything else, but they still feel the matter that is around it. So when neutrinos are coming out of the sun, for instance, they feel the electrons that are around them, and that has an effect on the probability of oscillation of the neutrinos as they go through the Earth. So it's not as simple as what I showed, but it is very similar to what I showed. The end result is that the neutrinos acquire a different mass as a result of the drag force that they experience while they are traveling in a dense medium. And that in itself changes the probability of oscillations. It's being worked out, and it's actually one of the best results in the field. That also happens for neutrinos inside the Earth, inside supernovas. And you're talking about the frequency of oscillation also is it maintained over astronomical distances? It is in the sense that they traveling neutrinos after they leave the sources and travel for billions of light years, they won't hit anything else. They won't go through matter. They're traveling in vacuum. So in that sense, once they are made in, say, one of these supermassive black holes and they leave the region where there's matter, they will travel in vacuum for 2 billion light years to us without hitting anything. So there's nothing in between that will modify their oscillation frequency until they reach Earth, and they might actually have some interactions while they're going through the Earth, but not in between the sources and us.
Okay, thanks. So since I think I don't see any more questions, can you just comment about the future of
Yes.
the experiments that you have been showing? So what is next?
So what's next? Fortunately, there's a lot of next. So yeah, I briefly commented on the detection of these we call them ultra high energy neutrinos. Before going there, I also want to say that there's many different experiments that are getting built now or being designed now to detect these neutrinos even better and to make improvements in the measurement of the neutrino oscillation parameters. So the parameters fixed by nature that control the oscillation frequencies, the transitions between the flavors, etc. Because the greater the precision with which we measure them, the better the answers that we can get to these open questions that I showed regarding the nature of the neutrinos. So that's going on, and that's going to come out within the next 5 to 20 years. There's different things that will be turned on at different moments. Now, regarding these very high energy neutrinos, ultra high energy neutrinos, those, as I said, are difficult to detect because the flux of the neutrinos that reaches Earth is super small. In fact, this is just one example. It could be even smaller than that. And we don't know how small it is because these neutrinos are being made by cosmic rays, not inside, so by protons, not inside astrophysical sources, but by protons that have already left the sources, are traveling towards us. And in between the sources and us, they interact with the cosmic microwave background. This is the relic microwave emission from the Big Bang. And when they do, they undergo some processes that give rise to neutrinos with ultra high energies. But how many neutrinos are produced depends on the properties of these cosmic rays. And we don't know what their properties are with sufficient precision to make a precise prediction of the flux of these cosmogenic neutrinos of ultra high energy. So this could be a lot lower, and that's a challenge of detection. So as I said, there are a few things that are going on that are targeting those experiments. One is an extension of the ice cube detector, the detector in Antarctica. So what you see here is the array of strings that are inside the ice. But there's an extra array that is being planned. It's called the radio component of ice cube Gen 2 that is going to be, you see over here, these are antennas that are buried inside the ice, not at a great depth, but close to the surface. And what happens is that when a neutrino comes in and interacts in the ice, it creates a particle shower that makes light, and the light is picked up by these photomultipliers. But it's also making radio, and the radio travels even farther inside the ice than light does. And so the radio can be picked up by these antennas over longer distances. And it is at the ultra high energies where this radio emission becomes important and observable. So this extension of the detector is targeting those ultra high energy neutrinos, and it's doing it in such a way that there's a fairly decent chance of detecting them within the next, let's say, 20 years. There's other detectors which I briefly showed. In this case, the neutrino this neutrino interacts slightly underground, slightly below the ground, creates a tau. Remember the heaviest cousin of the electron. Tau decays, now not inside the ground, but in the atmosphere, creates a particle shower that again creates radio emission, and the radio emission is picked up by antennas that are not underground anymore. They just are lying on the surface, in this case on a mountain. So we're involved in doing this. And there's other possibilities. So these are all detectors that are being planned in different stages of construction and funding. What I want to express is that there is plenty of activity in designing and building and funding these experiments. So the future is pretty promising for detecting these very high energy neutrinos.
Thank you very much. And so I think there are no more questions. I don't see any new one in the chat. So I really want to thank you for your time today and for giving us this very nice overview and summary about historical experiments and theories about neutrinos, and about the future of neutrino physics, and also of multi-messenger astrophysics. So I really thank you very much, and I hope and I'm sure that many people were interested into this, and Marco is typing that we were more than 200 people connected for this seminar
great.
today. So thanks a lot.
Thank you. I was very happy to do it. And again, don't forget we have this school. So if you want to know more about neutrinos, by all means, go into the webpage and contact us. We'll be very happy to have you over or online.
Thank you so much. I think there will be students interested into this. And thanks a lot again. And for all the others, see you soon to the next TMS webinar next week on Thursday. Thanks a lot, Mauricio, and thanks to everybody for attending today. Bye-bye. Have a nice day.
Bye-bye.
Ciao.
Ciao, everybody.